Uh, hi, good evening, all. I hope you can hear me. Can one of you confirm?
Yes, yes.
Okay, okay. Okay. So today we'll see some, design of LNA using ADS. How to do that? Steps I will explain to you. Before that, do you have any doubts from the last class or theory class of amplifier as well as the previous portions?
Actually, I am trying to do the assignment, but the
Okay,
results, sir, but the results are not coming.
coming.
Yes, sir.
Yeah, that might happen. Not coming means in the sense, are you getting some efficiency or not at all? Like, how close are you?
Sir, actually, the simulation is being done, but
Mm-hmm.
sir, how to get the results? I am not getting actually means the efficiency and S11 versus the length. So the
Mm-hmm.
efficiency, how will I have to find out? Means P out by P in into 100.
Mm-hmm.
So, so actually I am also able to write the equation of efficiency in the equation. So after
Mm-hmm.
that means the in the graph to plot the
Mm-hmm.
efficiency option is not there actually.
See, just for I think you are the same guy who told me last week also, no? Right?
Yes, sir. Yeah, yeah.
Yeah, I told you that you do first what same example what I have shown in the class. Did you do that?
Yes, sir.
That also you are not getting.
Yes, sir. What you have shown in the class, that
Hmm.
put that energy harvesting circuit, I have got the result.
That you have got the results means you have got the efficiency.
Yes, sir. Yes, yes.
Then you know how to calculate efficiency, right?
Ye- Yes, sir. Uh,
Okay, then
but sir, in here in the assignment,
uh,
this efficiency I am not getting means how to plot in the graph. The efficiency means
okay.
in the by the equation I can write, but I
Hmm.
am not getting in the graph. There is no option to plot.
Okay, so they are plotting versus what? Frequency or input power? What are they plotting?
Yes, they are plotting actually. mm, the option is V out and I probe.
Hmm. You can show
Yes.
me your screen, then I will understand it better.
Okay, sir. Okay, okay. Sir, so I will try by using my laptop. Now
Hmm.
I am doing I am in the meeting by phone. I am the, please give me sir some
Uh,
time.
okay, okay. Then you show at the end of the class. Okay, you set it up by now, by the time of this class. Okay, so we'll come at the end. Okay,
Okay,
yeah,
sir. Okay.
yeah. And anything from the amplifier? Did you study amplifier portion at all?
Yes, sir. Actually, sir, in my office, I am designing the amplifier. So it will be little bit means it is means theory is actually known to me.
Okay, no, 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 that's okay. I did not mean specifically for you. I meant for everybody. Okay, you can mute
Okay,
yourself. Yeah, yeah,
okay, sir. Okay, okay.
yeah. So others, all others, do you have any doubt on the amplifier portion? Any theory or any confusion? Nobody. And I saw only three people submitted the previous assignment. So that's a bad thing. That means you are not able, you're not even understanding this previous assignment. So you have to do more efforts. Okay. So the previous ones were easy. Okay. Now to do a full paper, I know it is little bit difficult, but it can be done. So you have to give more effort to it. Anyway, so there will not be any more assignment. And just to tell you, this is the last class. Today is the last class of this course. So if you have even any more doubt and all, you can contact me through mail, only through mail. Okay. And that's all. And there will not be any assignment. You complete this one and that's all. And it is up to you if you want to do anything on amplifier. Okay. And again, same thing. I will tell you, like if you want to, design amplifier also, do the same thing what I am doing. Start from there, and then you go to any other transistor or anything. Okay. But before that, any other doubt? Anything?
Sir,
Yes.
the switch concept what you have mentioned in the previous lectures,
Mm-hmm.
is it the design present in the ICs?
Design present in the IC means which IC, which design?
Switch, we have a switch IC in the market.
Uh-huh.
Suppose
You may no, no, I didn't get. Are you talking about the switch or the amplifier?
switch.
Switch means I showed you SPDT switch SPST. Are
Yes,
you
yes,
talking?
sir. Yes,
Yes, yes.
yes,
Uh-huh.
yes.
Okay. Yeah, you can get switch also. Yeah, switch might be already available in the market. Yes.
Can I relate this design to the IC? Means
No,
inside the
obviously,
IC?
see, no, no, no. They won't show you the design, right? They will just give you a brief overview or something. You can make your own design. That's why the course it is, right? Hello? I did not get your question. Like, yeah.
This is just for simulations, right? If
Just
you
not.
want to
Uh,
implement, you have to
uh-huh.
do in cadence, like,
No, why in cadence? You can do in
okay.
ADS and design. Yes. What is there? Oh, you mean
ADS
at the
is just
IC level?
yes,
Uh-huh.
sir, yes, sir.
No, even see, this all I did not show you any IC design, right? I showed you in a PCB how to design all this. You can design in a
No,
PCB.
okay.
Yeah, right. I never, discussed anything about any IC or anything. I all the designs I showed you how to do on a substrate in ADS.
But it comes under PCB, right? If you want to design total IC, so we have
Hmm.
to use for
No,
simulations we
you
can
see,
use
uh,
ADS.
no, 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 no. That's a very wrong conception. Whatever we are doing, we need PCB for it. And for that, we can directly design using ADS.
Okay.
Yeah. Anybody else? Okay, okay, okay. Yeah. So, okay. So we'll go into the ADS part quickly. Okay. So for the design of LNA, so the basic steps are first we start from a transistor. Okay. We take a transistor of our choice and we decide what will be the DC or bias values. Then first step, as we discussed last week, we go to stability analysis. And then comes to impedance matching and finally design of bias lines. And next also we look into noise figure analysis. Then we redo all the steps with together with noise figure and we come to final LNA design. Okay. So let us see for the DC bias, what will be the steps? So first thing is if you look into any transistor like BJT or HMT, so what they will give you in the datasheet is IC versus DC plot. And so from there you have to see like which particular point you have to operate. So selection of the operating point is one important characteristics that you can look into among these ABCD points, which one you want to operate at. And the other thing is how the biasing will be done. This bias network topologies itself is another important point. So as you see in this table, which is taken from this Gonzalez book here, so multiple topologies are possible. One in one case you can like in this MOSFET, Either you can bias through the gate or drain, or through gate or source, or all any two of these three combinations. It depends on what kind of characteristics you want. As you see, A, B, C, the all of them have the same LNA as well as high efficiency. But in this D and E, what you get here is like you here the efficiency is lower, but because you have a source resistance connected, that gives you some flexibility in adjusting the gain. So you have to decide what of these things you want. Accordingly, you have to select a bias network topology. Okay. And selection of the operating point is another thing you have to decide. So when it comes to ADS, so how do you get these things is like, generally in the ADS library itself, there will be some of the, the models of transistor will be already loaded or available. Okay. Although most of them are quite old, but you can still use some of them. So just like this one, if you see, this is a BJT NPN model, which shows the important thing here is this is stored for a particular VCE and IC value. Okay. So it's not for all the bias condition. So they give you for a one particular VCE and IC model, and ultimately what is stored inside is a S parameter model. For this VCE and IC is this. At the right side, let me take the pointer. Yeah. So this is the model what you see in the in areas inside. It gives for a frequency range of 100 megahertz to 4 gigahertz, let's say. So this is MMBR. I think it's a Motorola transistor. It used to be old one, and so I looked into a data sheet. So this is what they give. At the left side, if you see VC and IC is given. So for multiple VC and IC, there will be big table there in the data sheet. Okay. But for only one here, 6 volt and IC is 10 milliamps is all is taken here. You will find in the in a ADS model. Okay. So what it shows for all these defined frequencies, S11, S21, S12, and S22. These four models or the four parameters, magnitude and phase. That is what is given, and the same thing is inputted into the ADS model here. If you this is the taken from ADS model inside. So I have went inside the ADS model and taken this snapshot. So if you go into that, the same data will be you see find it inside. Okay, for a particular VC and IC, and what would be this SNP file? Okay, SNP means because or S2P means a matrix of four different S parameters. That is what you find. Okay. So now if you see here, S21 is quite high as expected because it's the amplifier we are working with, and S12 you see it is quite low. Okay. It's not completely unilateral. That means S12 is not completely zero, but it is quite low. You can approximately make it as a unilateral for some frequencies. Okay. And S11 and S22 as you see, these are also given. So basically what it says, this S parameter model is stored inside ADS. But in ADS, the thing, this is just for an example, okay? But for any new transistor or anything, you might not find any model in ADS, okay? So this task is for yours. If you just pick a new transistor from market, you have to pick up their data sheet and you have to create this model here inside. Just nothing else, is just this data you have to put. And then you can create your own transistor here. So these are a linear model because this parameter is a linear model. For a particular biasing only you get it. Okay. There's another possibility is the better option is a nonlinear model. So when if you for a transistor if you have all the internal parameters given, then you can do all this analysis in the in the ADS itself. For defined bias conditions, you can do a DC analysis and find out this S parameter. But unfortunately, most of the transistors you will not find it. Okay, they mostly they I could not found the nonlinear model like diodes, but you will only get this S parameter file. That is what you have to work with for a particular biasing. So that works for our LNA because we don't do a power analysis like power amplifier. Okay, so in that case for power amplifier It is very crucial to have a non-linear model. But for our LNA design, only linear S parameter model is quite fine. So is this part clear? I hope I am recording this. Okay, okay. So, okay, let me go back to the presentation. Yeah. So now that these things are there, so as I told you, first part is stability determination. So I will go through this one quickly once, then I show how we are doing in ADS. Okay. But the theory is the main, you have to first understand the theory. Otherwise, directly if you go to thing, the ideas, it is like lot of Smith charts. As I told you, you must understand Smith chart properly because all the analysis heavily relies on Smith chart. So if you know the theory, this will be a cakewalk. Okay. So the first step I told you, the stability determination, we take this K delta test. So where for unconditionally stable, what we need? K should be greater than 1 and amplitude of delta should be less than 1. And this is, in this model here, it shows how it can be calculated in ADS. Okay. So this stability factor right side, image. Most of these things gain stability and the circles, stability circles. All of these, there is a option by default. You can just click on this and plot it. So your task is more on you have to understand and analyze. Okay. You don't have to plot yourself or anything. And as I told you, there are multiple gain plots here. Okay. So which one is important you have to see. So as I told you, unconditionally stable mostly does not happen. And that for that you have to satisfy k greater than 1. But what we generally get is a conditionally stable. For that k will be less than 1. This k parameter will be less than 1. And for that, for unconditionally stable, the important gain parameter might be Gmax or maximum available gain, which can be, which can be defined as this S21 by S12 in terms of K, where K is greater than 1. And it happens only when conjugate matching happens. Okay. So input and output both side is matched. Transducer power gain we already discussed last week, which will be, determined by this average. But more often, what we actually, uh, get as a amplifier is a conditionally stable device. So where k is actually less than 1, so there the gain parameter is maximum stable gain, or which is called GMSG, which is written as a ratio of S21 and S12. So maximum gain, transducer power gain, and maximum stable gain, all these three are very important. So this we'll discuss there, we'll see in the analysis. Okay. So now before coming there, let me show you. Yeah. So I hope you can see my ADS screen. Okay. So this is one BJT. Okay. So this MMBR Motorola model, same thing I told you. This I have taken from the, the parameter here itself. Okay. So yeah, by the way, uh, how you can get this? See, the thing is in ADS, you can unzip a whole model. Okay. Let me see if I can show you. Import. Yeah, I just wanted to show you. So where these models are available, let me see. Open. It will be here somewhere.
I think that green bar from the
Mm-hmm.
like component net search bar is there, not just adjacent to the right one. Huh? That one I think.
No, that one is there, but I already imported here myself. So
Okay.
there is another option. That is what I was looking. See, this is already I have imported here, so you can find all the different components available here. That I can show you.
Okay.
But yeah, this is because already I have unzipped the folder here.
Okay. Now you're trying to show how to unzip and
Yeah,
add.
exactly,
Okay. Okay.
exactly.
Okay.
Yeah.
Fine.
Or was it later? Let me see. Some. Anyway, so I guess not finding it here, but it will be here somewhere. So I'll just show you, from my folder itself where it is. Download. Hmm. Okay, so this is the ADS file. Okay, where my ADS is installed. So somehow you can go inside this. Okay, from there you can access this folder. And
I think it is from design in unzip.
yeah, that is exactly what I was looking. Where is it? Designer. Option. Yeah, I think here, right. Because I was going inside that it was not. Yeah, right. Yeah, it is here. Design unzip kit. Okay. This is outside the folders. I mean, outside the design. Okay. So thank you, whoever pointed it out. Yes. Yeah. So here you will find something called, let me see, lib. Lib. Yes. Is it not? OA libs. Sorry. Yeah. So this OA libs inside this, design kits, you go here inside OA libs. So here you see there will be lot of components. Okay. So this component lib, here you see lot of, zip files are there. So not only about transistor, you can see there are passive SMT vendor, microwave transistor, and there are like high frequency diodes, and a lot of different components are there. Even some system components are also there. So you guys, just look into this and play with this. But for now, here the important what is needed is this microwave transistors and RF transistors. So when you do this, they will give you, how to unzip. So here inside this, I have unzipped all these three new folder 3, 4, 5. You can also unzip one of them. And when you do this, then it will appear in your file. Okay, in the design file here. So then when you unzip, this will appear here in this read only library S parameter. Okay, so here you see there are like lot of options from multiple vendors. Okay, so this one is Motorola. You see, in all of them, as you see, they're all mentioned for a particular bias. It's not for all of the bias condition. Some particular bias condition, you get the model. So you can, just click and it will appear here. As you see here, just like this. You can just click and bring it here. So, but the important thing to note here is that these are just for your learning. Okay, you can just learn starting from one of them. But finally, if you have to do a practical design, most of the cases, you have to design this folder yourself. You can even make this yourself. It's nothing but putting the values in a correct format. Okay, so that is. So now let's see what we have done here. So this BJT we have picked up. So at the very simplest one, we start from just connecting a, the 50 ohm termination at two ports here and here. So this resistance in between here, I have deactivated. I'll come to that. What is the function of this? And what are the sorry, what are the things we have activated? Gain plot, maximum gain. All these things you will get from the S parameter model here. All these things you will get here inside. Okay, gain, stability, source stability S step, L stability is the load stability. Okay, stability factor calculation, and we have even taken another equation for calculating delta. What is this delta? This is K delta, from that delta. Stability factor will give you K. So if you put all this and do the S parameter run, then what happens? You get this plot here. Yeah. Okay, this is one. See, this is the stability plots what we have seen in the class. So right side is the load stability and left side is the source stability circle. So now what it happens, as you see, the stability circles are inside the Smith chart. So what does that mean? Can one of you tell me? What does it mean? Anyone? I hope you are with me.
Means it is conditionally stable.
It is conditionally stable. Exactly. It's right. So it's not stable. That means or conditionally stable. So in the both a load and source circle, if you remember from our class, they should be actually outside the circle, this Smith chart. Then only it will be stable, unconditionally stable. And here
Hmm.
at the top, you see what are the parameters. So here, as you see, we are trying to design for a particular frequency that you should keep, keep in mind. As you told you, most of the cases we will design around a particular frequency and narrow band. Okay, it's not we are not discussing a wide band design. So for that, the conditions will be different. So here, let's say for 500 megahertz, we are trying to design. So what from what we have, the parameters we have deducted, maximum gain, magnitude delta, and stability factor. Stability factor is K. Here, as you see, K is less than 1. So that means if K was greater than 1, then only it will be unconditionally stable. So as this parameter shows, it is not. Okay. And one important thing, these equations, as you know, the MSG in maximum stable gain, you can calculate here. So generally you draw this S parameters here. Similarly, you have equations tab here. So you can write your own equation and it will be calculated and shown in this plot. Okay. So now that it is not stable, what can we do? Coming back to our design here or the PPT here. So now see what happens. So when it is not stable, we have to do something. Okay. So one option is that we can go with a unstable design itself, but we have to very carefully, treat or find a zone where it is unconditionally stable, but still we can work with it. But a better option is can we make it somehow? Can we add some component here to the transistor and make it stable or conditionally stable? What is these options? That is what we are going to look now. Now see carefully. So what happens? I just told you this unstable or conditionally stable happens only when there is a chance of oscillation or negative input resistance. When that happens, when either real part of ZS and Zn, ZS and Zin is nothing but here if you see source and input resistance of the transistor together, real part of it, or in the load side, real of Z out and ZL are less than 0. If any one of them are less than 0, that means a negative resistance, it has a chance of going to oscillation that makes it unstable. Okay, so now how can we do it? How can we make it stable? So the simple logic or the most easiest way is this: we can add a resistance, intelligently, or with some analysis, we find out this resistance value so that we can push it back to the positive region. See, now it is in negative region, right? Because it's unstable, we found out it is negative. So we can add some resistance to it so that it can become greater than 0. Or at the boundary, it will be equals to 0. So we want to find out that region where it will become 0. Okay. So that now our next task in design is we have to find out here. If you see this 29 ohm resistance here, let me take the pointer here. We have added, we can add a series resistance at the load side or a shunt resistance at the load side so that it will become greater than 0, or at the boundary it will become equals to 0. Real part of the impedances will become equals to 0. So this is done through some intuitive analysis in Smith chart. So this is a Smith chart again taken from Gonzalez. So right side is the output stability circle here, this one, and left side is the source stability circle. Both of them plotted in the same Smith chart. Now, let's say we can do either in the input side, add a resistance, or add a resistance in the output side. What will we do? Let's see. We prefer, let's say, do a shunt resistance at the output side. Okay. So now what resistance value do we add here? This calculation is done through this. So because we are doing in the load side, so we have to look into output stability circle or load stability circle here. How do we do? See, in this boundary, let's say this is the point where, let's say this is for 500 megahertz calculation, what we are doing. Okay. So we have to find out what is the load resistance here. Okay. This load resistance, if we find out, then we can add the same resistance or same admittance here so that it will be like how. Let's see in the S parameter chart. From Smith chart here, how it is easy. As you know, Smith chart, this side it shows admittance chart, and if you take in the this side, in the opposite side, it is resistance chart. Now we are interested in admittance chart. Okay, so that means this one and this one and this one, these are admittance chart. So now here you see we are taking here in this point. Why this point? Because this is the frequency we are interested in, where we want to make it stable. That means this point has to be pushed out of this Smith chart. So how do we do this? From here and this admittance chart, we find out what is the admittance value here. So this corresponds to this circle, which is 0.1. And from this 0.1, if you divide by 50, you get the admittance. Or correspondingly, it gives you a 500 ohm. Okay. So as you see how it is important to understand the Smith chart. Because this point overlaps with this admittance circle, that tells you what is the admittance point here, 0.1, and or you divide 50 by 0.1, then it becomes 500 ohm. So that means at this frequency point of our interest, we have a negative resistance of, or negative admittance, negative resistance in parallel connected is 500 ohm. So that gives us the intuition that if we add another 500 ohm in parallel, that will lead you to this real part of this to 0. You understand our thinking or intuition? Because of this 500 ohm at parallel at this point we are analyzing from here, that makes it less than 0. So if we add another 500 ohm, that will give you to the boundary or lead you to the real part of the resistance seen by the load to 0. If that happens, what will happen? Then this will be pushed out to the boundary here. This load level circle will be pushed out to the boundary. That will mean we will get a stability. Is this point clear? You have to analyze very carefully, then you will understand. Okay, is it point clear?
Like initially you said like at this point we have point one for from the output load circle, right?
Yes, this is the output load circle.
And
Yes.
that is the admittance, normalized admittance.
Yeah, normalized admittance, what we are calculating, right? Yes.
Okay.
So you
So
understood why we are calculating admittance, because we are interested in a parallel, putting a
parallel,
parallel resistance. Yeah,
yeah.
yes, yes.
Like that means like that is already due to our FET alone because of that BGT alone.
Exactly, exactly. Yeah, right. So we are now
Uh,
first, as I showed you in the ADS just now, we are doing only a transistor analysis. Then we see which region it
okay.
falls. Okay, yeah.
Mhm. So
So, hmm,
then actually, because we are seeing 500 ohms almost due to the transistor alone, we have to
hmm.
add additional 500 just to bring it into the um, negative region or positive region. That positive resistance region that is little.
So
Can you just
see,
clarify?
yeah, yeah. So what I am saying, the conditions for instability is this: real part of the resistance seen is zero. Sorry, real part of the resistance by the load side is less than zero, which
Hmm.
is in our case happens to be minus 500 ohm, which you see here 500 ohm is actually a negative resistance seen. Why I am
Okay,
saying
by the amplifier, by the
exactly,
transistor.
because it's unstable at that point. Okay.
Hmm.
So because at the load side we see minus 500, so what logic says? If we add another 500, it will become zero.
Hmm. Okay.
Right. So that's why at the load side we are choosing to add another 500 ohm in shunt.
Okay. So then it will become zero only, but it will not
It
become
will, yeah,
positive.
exactly. It will become zero. That means we are pushing this load stability circle just out of the boundary. Just
Okay,
out
to
of
the
the
boundary.
Smith chart. Exactly. We are trying to find the boundary condition here. I mean, it is
Okay. Understood.
zero means it is at the boundary, right?
Right,
Boundary
right.
between greater than zero and less than zero.
Yeah, yeah. Anything greater than that, it will become unconditionally stable.
Exactly, exactly. Right, right, right.
Okay. Yeah.
Yeah.
Thanks. Thanks.
Yeah, okay. And even before that, who are not so, who did not follow the previous class. So if you see this stability circles, I'll give you a brief outview. See, anybody who is afraid of Smith chart, many people are, I know. So you have to always understand any plot, what you should look for is what it is being plotted. What are the X and Y axes? Okay. So I don't know if you know or not. Smith chart, we plot gamma. Okay, gamma is the reflection coefficient. So, and because it's a circle, it has also some x-axis and y-axis. So, can anybody tell me what is the x-axis and y-axis in a Smith chart? What do you plot?
Reactance
Normally,
and
x-axis
resistance
is
circle.
resistance and y-axis is like reactance or admittance.
No, it is related to gamma. As I told you, we plot gamma only here. Gamma is reflection coefficient, and you have to remember it is a complex number. Okay. So if you remember the
Mhm.
circle, if you plot a complex number circle, what happens? What will be the real and x so now, yeah, now I only told you. So for a complex number, if you plot, what will be the x and y axis? It will be the real and
Real
imaginary
and
number.
imaginary. Yeah.
Exactly. So for a Smith chart, which is so, there are a lot of things inside. It's very, very useful if you actually look into it. But at the core, it is nothing but a plot of gamma, where the x-axis is the real part of gamma
Real
and
part.
y-axis is imaginary part of the gamma. Okay, that's all. It's nothing else. Okay. And from that, you can find out input impedance and VSW or all these components. So now what is important here, what we are doing in this, load side stability circle, what we call it load SC stability circle, and source side stability circle. Both of these we are plotting. So these circles also nothing but a plot of gamma L. For load side plot, we plot a gamma L. That means the gamma reflection coefficient seen here looking at to the load. That is what we see here, plot here. Okay. So for that we find some, the center and resistance, and then we plot on here for a gamma input Smith chart. And then we try to find out if there is any overlap between them. If there is overlap, that means there are some zones where it is not stable. Okay. If there is no overlap, that means inside this circle, it is unconditionally stable. Okay. So only thing is inside this load stability circle, it is unstable. That is what you have to remember. Inside this circle, it is unstable. Outside, it is stable. Similarly, at the source side, if you look, so this is the circle where you plot gamma s. So gamma s is the plot of this circle. Inside this, it is unstable, but outside this is stable. It is stable. So ideally, we need to have a plot like this. Okay. But that does not happen generally. Just what we have now, we'll go back to there and see. See what we had. This is the load side and this is the source side. Both of these cases is inside. That means this zone, this overlap zone here, it is unstable. So what we want to do is actually want to push them to the boundary or even outside. Okay. That is what we want. Even if we can just put it to the brink of this at this point, then also inside this mid chart anywhere we will get stable. So we want to do that, just that. We don't want to push into this level. Okay. Even just by, the boundary condition will also work for us. Now see, now how do we do it? The same analysis we do it here, just like this. From here Smith chart, we find out what is the, the admittance here. From that, we add a shunt resistance. Okay, now coming back to this, here we can do both ways. We can add a resistance at the source side as well as in the load side. Now, can you tell me why we don't do in the source side? Why we are choosing to do it in the load side?
It will give
Because
me a better
mostly
view.
source impedance will be already defined, and load is a variable thing in our design.
No, not exactly. It has something to do with noise figure.
Okay. Yeah, noise
It
figure
has
normally at the input is determines the complete system's noise figure. So if we add more resistance at the input side, the noise figure will increase. Means like at the
Exactly.
input
Not
per
only
input
increase,
side.
it will be amplified with the amplifier,
Amplifier.
right?
Yes,
Yeah,
yes.
exactly. So that's why we are adding in the load side. See, everything has to do with some logic, okay? So you have to
Mhm.
understand step by step. That's why we are trying to do in the load side, even in the shunt condition. So now
Okay.
here, similar to this, we find out here. From here, this load stability circle, if you see this red plots here is means the admittance circle. So if you see here corresponding to our 500, you can take a marker here and put here. Okay. So from here, you can find out what would be at your point, what will be the corresponding admittance. This is the, it gives you corresponding to your this impedance Smith chart, but you can also find out for admittance. So it will be, as you see this one, this red dot is 0.5. As you go to this extreme, it will close to 0.1 or even less. Okay. So if you take it 0.1 or less than 0.1, so that means 50 by 0.1 or close to that will be around 400 ohm. Okay, or 500 ohm. It will be less than that. So now we choose to add that. Now let's go back to that design. So that's why see here we are adding a shunt resistance of 390. So we calculated this from the same method. Now let's activate them and do the analysis again. See now, see the magic happened. Just see how this worked so far. Just we were by calculating this, we are able to put both the stability circle to the just the exterior of the Smith chart. That means now inside the whole Smith chart, everywhere you work, it will be stable. Okay. So now you see the stability factor is 0.999 because that is at the brink of 1. Okay, that's why. Yeah, anybody is asking anything?
Yeah, one doubt. Now, actually, it's marginally stable, right? Because it's almost at the boundary.
Almost at the boundary. No, but that is fine because we will operate inside the Smith chart only. Because as you
Mm-hmm.
know, inside the Smith chart means reflection coefficient is less than 1. Okay, that is where we will actually work. So this is fine for us.
Mm-hmm. And suppose if we increase the resistance even more, will it
Yeah,
cross beyond this and
yeah, it
maybe
will
it will be
cross beyond
outside the
that.
display, right?
Yes, yes, it will. But
And
there
we
is a
cannot
catch
even
here.
visualize.
No, no, you can, that will be better, but there is a trade-off here. See, just
Okay.
because we are adding a resistance, obviously we have to give, give away something. What we are doing,
Loss.
we are actually giving up some amount of gain.
Mm-hmm.
Okay. So if the amplifier was, or the transistor was itself stable without anything, it would have given us better gain. So
Mm-hmm.
because we are now putting some resistance here to make this stable, we have to give up some gain. That is what we are doing. So now if
Okay.
you want to put more resistance, it will even reduce the more gain. Okay. So that's why we stick to this boundary zone region.
Okay. And this thing, whatever the maximum gain which is displayed here, is it a
Hmm.
kind of P1 dB gain or like a maximum under saturation also?
No, this is maximum stable gain means. So what is the maximum gain is possible to achieve from here? So you see, MSG is for answers. And as I told you, maximum gain here,
Mm.
this is what is the overall gain you can achieve from the amplifier. Okay, this is this. But what is important, more important is this MSG. We'll come to that, next plot. Because you see, there are multiple factors of gain. So we will come to that. Okay. Yeah. So for now, I want you to understand how this stability is done. So now
Okay.
let's
Yeah.
go to that part. Let me see. Yeah. So this is the plot. As you remember, we plotted, put multiple gains and all here. This is here. So plot versus frequency. First of all, we plotted three gains. Maximum gain is this one. I will go back to again here. This maximum gain is this one. If it was stable and conjugate matching is there, then this is the maximum gain we could have achieved. Okay. But because it was not stable, so we have to go with is maximum stable gain, MSG. Okay, this is this. And what even more normal is transducer power gain or GT. So now these three has been plotted here. GT, MSG and maximum gain. So all here it is given. Okay. So as you see, maximum stable gain is here more. Is so what you could have achieved at maximum, but because in our case it is not stable, we are actually able to achieve a little bit less than that. Okay, but at the C at the 500 megahertz where we are getting here again, here it is both of them, the red is the maximum gain and MSG goes to same value. These two plots are they are converging here, MSG and maximum gain, because if you see here, this is maximum stable gain is defined for k equals 1. Okay. And here also maximum gain we have is dependent on k. If you put k here, both of them becomes same. If you put k equals 1, maximum gain and maximum stable gain both become S21 by S12 ratio. Okay. Now because we are able to push them out backside, so we made it marginally stable. That is k equals 1. So that's why at 500 megahertz, both of them becomes equal. Okay. That is because we have put the resistance now. Okay. In other frequency, it might not be. As you see, they are different. And the same thing happens here. As you see in the this one here, this is a plot versus k versus delta. K is stability factor rate plot, and delta is that delta from the Rolle's condition. As you see, 500 megahertz, we are marginally stable. K is equals 1 and delta is less than 1. So Below 500 megahertz, as you see, it is even less than 1. That means it's not stable. At 500 or above, it is stable. Okay. Any question here? Okay. So now I suppose it's fine. Now let's go to, now the stability you have determined how to push out to this and get some stability. Then what will be the next consideration? So next consideration is how much gain do you want? Okay. So for that gain, we will come to that. No. So you can achieve for given stability, as we told you, some gain you have to give up. Then you can achieve multiple gain and stability together. That analysis we do through a gain circle plot. So gain circle is also like, it is a circle, it shows. So in which region, which gain you can achieve. Okay. So these are similar circles. So those are all done through Smith chart. And why the main condition is here, you can't actually achieve maximum gain most of the times because, the correlate match does not happen most of the times. There are lossy elements like resistance and they are potentially unstable. Okay. So that's why, so we give up something here. Let's see how we do that. So the circuit remains same, everything. So these are all same. Just, let me go to the gain circles here. Okay. So the gain circles you can put here. As you see, what are the gain circles? Three of them we have plotted, huh? Yes. So what these three are the three defined colors. So you can actually put gain circle. First one is maximum gain, is the blue one. Okay, it shows here. If you make a circle of maximum gain, as you see, it is actually going out of the plot here, going out of the Smith chart. That means it is becoming unstable. If you take maximum gain minus one circle, then it becomes this the pink one. It has some zone inside chart. And if you do maximum gain 1 minus 2, that gives you a bit even better, or more larger circle. So you have more flexibility or chosen one. So that means if you sacrifice 2 dB of gain here to the maximum gain, you can have a better stability. You can operate inside chart. And what is the load stability circle here? You see, this is the green one. If you see here, green one is written here, load stability circle. It is at this boundary. So definitely you have to operate inside here so that it will be stable as well as you have some gain. That's why we choose to operate here. Maximum gain is 22.4. What you can get here, let's say we choose here. That means to around 20 dB. See, that is what we are getting here, 20.442. Is this clear? How we are, deciding the gain and the stability circle?
Can you
Can
explain
you
that
explain once?
equation part like the you mentioned GP circle underscore one equal to GP
See,
underscore circle.
this is actually we are doing nothing. You have to just put this in a here. I told you you can put equation here. Yeah, see here. You have to define equation here, and you have to write the same thing. GP circle. Yes, S is it means the Smith chart.
Mm-hmm.
Maximum gain 1. That is what we already have defined here. Maximum gain 1.
That blue circle. Okay.
Yeah, yeah, yes. Blue circle. No, no,
Minus.
not the blue. Blue circle is this circle. GP circle maximum gain. Okay,
Okay. Mm-hmm.
I think you have see before coming there that we are coming to. But how do we get this? So I am saying these equations you have to define here. GP circle maximum gain 1, 2. You have to write the same things. These are all defined in ADS. You have to use their language. Okay. You can go maximum
Uh,
gain minus 1, maximum gain minus 2, up to whatever you want. And how many points? These are the number of points.
okay,
So if
that is the
you
point. The last one.
exactly, you
Last
see,
step.
if you even look inside, they will give you from here help. Okay. From
Mm.
anything you just go to help. That's it. So now that these are defined, and if you go inside, it will come. These plots will appear here, and see at the here it shows which color is what. These indexes are given here. So first one is blue circle is the maximum gain circle. So it is almost, it is almost out of this Smith chart. That means you can't operate here. That is the whole essence of this, this study. So you can get this, stability as well as maximum gain. Now, how much gain do you have to sacrifice? What can you do? So that is what we are doing. The pink one is minus 1 dB and the orange one is minus 2 dB gain. Okay, and stability circle is the must because we are doing with stability analysis. So when you do, then you find out that, we can sacrifice 2 dB gain and we can region operate in this way here. This is the M1. M1 is because this is the 500 megahertz, the analysis we are doing. So all we are doing for some particular frequency. Okay. So this M1 shows that. So now let's say we decide this point. Okay. Let's say this is our designated point, which is stable as well as we get some good gain. Okay. Now what is the next task of our design? Next task is getting the matching. So how do we do matching? First, we have to decide what will at this point, what is the source and load reflection coefficient, or accordingly, what is the source impedance and load impedance. That is what we have to find out first from this point. So you understand, right? First, we decided a point where we are happy. We get some gain, we get stability, and then we decide what should be the what is the impedance, source impedance and load impedance at this point. So that how do we do? For that we have another calculation here. So using the Smith chart, as you know, Smith chart here you see 0. This it shows what is the impedance value here. That is gamma L here at this point. Gamma L is M10. If you define a marker, this marker value M1 naught is the load resistance here. Gamma, or sorry, it gives you the gamma value, gamma L. You understand that, right? And the same thing is shown here also. So first thing of the marker is M1 naught is the gamma load value. Because why this gamma load value? Because we are doing this calculation from the load stability circle. That's why we can calculate gamma L value here, gamma load. So once this gamma load is done, from equation we can calculate gamma in. This equation is already there. You can go to the last week's class. If you know gamma L, you can calculate gamma in input. When you know that, so what would be gamma S then? It will be conjugate of gamma in. Because as you told, we want to do actually conjugate matching. So from this point, we come back to gamma load. We calculate gamma in, and then conjugate of this is the gamma source. So this is this point here. So gamma source is this point. So this is the point what we are going to actually find out. So once we know this source point, this is what gamma source, then our task is to design the matching network. Is it clear? Is this point clear for you? Yes, sir. Okay. So the thing is, see, all these equations are written here. You can exactly write the same equations here. Okay. You don't have much of a task to. Only thing is you have to understand the things. Our now see this is what we are trying to find out gamma S and gamma L. So once we know the source resistance and load resistance, now we have to design our matching network. So that is what I am coming to. See, it is taken from the same one. Okay, same network, similar network. So what we have here, as you see, we have here, let's say for this example, yeah. See this one, left side. Let me take the pointer again. Okay. Okay. So your task is to find out this is the point. What is your operating point so that you have the gain and stability. So let's say this is the M1 marker here, the black marker. We have chosen this point. So we know the gamma L, right? And from this same gamma L, we have found out, let's say gamma S also. This is the blue point. So now, sorry, no, gamma L and gamma S, load reflection and source reflection coefficient. And the corresponding impedance obviously can be found easily. Now our task is we have to design a matching network at the input side and at the output side. Why? Because ultimately our load is 50 ohm. And at this point, see, this is the gamma L. Okay. At this point, we have decided the gamma L. Okay. And this side is 50 ohm. So this task of this matching network inside is to bring this gamma L value to 50 ohm here. The corresponding ZL load resistance to 50 ohm. And here also, here I see source resistance of this gamma S or like a corresponding ZS source resistance. But we need a 50 ohm here to match. So we have to add another impedance network at the input side so that which will transform the 50 ohm to this ZS value. Okay. Now how do we do? Again, see, there are lot of things, lot of ways it can be done, and definitely you have a tool in the ADS itself. I have shown you in last topic, the harvesting circuit topic. That matching network design you can do just easily. But the thing is, you have to understand the theory here. So how to do this? There are multiple options here, as you see in Smith chart. So your task is from this black dot come to the midpoint, because midpoint is where if you come, that tells you your gamma becomes 0. That means you are matched to 50 ohm. So you can come here in multiple ways. You can follow this red circle or you can follow this blue circle. Here also at the source side, you can follow multiple ways. Many different ways you can do. So now your task is to see which is the optimum way, and here it comes the hardware constraints that you have to see. You can do with different ways. And not only the matching network, here is important task of even biasing. As you have to see, both in the input side and output side, you need biasing. That is what is shows here. So together with matching network, we will we will even, add the biasing network together. So if you see in the loads here, this example, you need bypass capacitor, DC block capacitor, as well as a RF choke. So either to, bias to block the AC or block the DC. That is the same concept we are, looking for the long time. Okay. So same thing. So now the task is you have to do intelligently so that both the matching network and the biasing can be done together. What are the ways? So generally there are two ways. One is you can do using RF chokes and blocking capacitance. You can use biasing, or even you can bias through the matching network itself. So that means you don't have to add extra RF chokes. How you do that? Let's see. Now we come into that analysis. So here you see in the load side and source side, we are doing two ways. Okay. So first thing is this whole thing is a matching network. This one here and this one. Okay. I will show you in ADS also. So before that, I will explain one thing. Let me see. Yeah. So the thing is, see, if you take this red plot, okay, the red arrow here, if you choose to this red arrow for matching, that means you are staying in a same resistance circle, but you are adding only a inductance. That means if you add a inductance, you can come from M1 to here, okay, or here to M1. So this is what is done in the load side. Okay. If you so now how can you add a inductance? The easiest way is you can use a lumped inductor, or might be a better way to do to use a high impedance line. Okay. As you know, if you remember for our the filter design, What also means we represented inductor with a high impedance line of some particular length. High low low pass filter was there, and a low impedance network or low impedance line, microstrip line, can represent a capacitor. So now here we are interested in adding an inductor that can be done through a particular length of high inductance line. That is what we are adding here. T lin of 80 ohm and some impedance. This impedance you have to calculate using that high low calculation. You have to go back to that calculation. So if you do that, then using without any other thing, without any other element, or even you can use a lumped inductor also, that will give you a load side matching. Okay, that is one way. Now that you add here, you have to bias. How do you bias here? You add a choke here. See at the load side, you add a choke, this one, and a bypass capacitor. What is the bypass capacitor here? You know this one. Yeah, this is the bypass capacitor. Sorry, huh? This is the bypass capacitor which has been represented as a RLC equivalent. Okay, which is this one, and the DC block here, because the DC should come only this side, right? Should not come that side, load side. So that's why this is the load. This is a DC block capacitor, which is also represented as a RLC equivalent, which is 200 picofarad high capacitance. So as you see, all of them has been represented like this because they considered a very realistic case. Any capacitor you take, it will come with some parasitic values that they have that we can actually consider. Okay. So this has been taken, and it requires a RF choke here. Okay. And even you can take the RF choke also with a high inductor value and the corresponding okay, R and C parasitic values. So here it means we are taking the first way, bias with RF chokes and blocking capacitor. That is what we are doing. Okay. So we need a separate RF choke and all. But another way could have been if we follow this blue path, we go using this path and then go there. Okay. So this way you need one series stub and another shunt stub. Okay. This if you will actually look into in ADS, tool or some here also, it actually gives you, it needs one series stub and another shunt stub. And similarly, what we have done here in the source side also. So source side, we have actually taken the second way. First is a series stub here, which gives 50 ohm. That gives only a phase shift. Okay. And the shunt stub, it represents a inductor, which can be represented by a shunted or a shorted stub, which represent a inductor. So now that you in the shunt arm, you add a line like this, we can actually bias through this arm directly. It does not need any extra choke. That is what we have been talking here. So bias through the matching network itself. That is what we have been seeing here in the this side. Because we have a shunt arm and this has quite high inductance, we actually we actually bias through this arm itself at the source side. But the blocking capacitor and the this bypass capacitors are there. That they will be there. But the RF choke you can avoid actually. Okay. So that is what I have been talking about. So here they are all grounded because the large signal values are grounded. We are doing S parameter or small signal analysis. But ideally, actual circuit, you will have your bias connected to this point between this and here. VBB, VCC. Okay. VBB point here and VCC point here. That is why it has been. And yeah, by the way, so this reference is very important. This you can look into this web page from Dr. Professor S. Long in UCSB. So, and his book is very important, very useful. It shows a lot of application in ADS. You can refer to them. Okay. Okay. Now are this clear? Is some of this clear at least? Yeah.
Uh, yeah, it's like normally like RF chokes we are now replacing with in the source side. with a shorted stub, no? I mean, it's like
Yeah,
not replacing, like that is serving purpose of our RF choke as well.
yeah, exactly, exactly. Yes. So that
Okay.
means intelligent. If we do things intelligently, we can do two things at once. Yes.
Yeah. For calculating that RF stub, like means like shorted stub,
Hmm, hmm, hmm,
do
hmm.
we have an option directly from ADS to calculate with the equivalent lumped circuit, lumped L
Yes,
value?
yes, yes, yes. It is there. If you remember in the matching, in the energy harvesting class, I have shown you in that demo that there is in ADS only you have a tool called matching. Even I can show you here
Like the
also.
even using the Smith's matching tool only.
Exactly, exactly. Same thing
Okay,
is
okay.
there
Actually,
inside.
I know like matching we can do with lumped elements, and how to convert that to stub.
No,
Actually,
no.
I am not.
In there also itself you have the option of using a lumped element. Sorry, using
Okay,
distributed element. Yes, you have
okay,
the
okay. We
same
have to
option
choose
there.
that.
Hmm.
Okay,
Yes,
okay.
yes. So only thing is this thing the concept should be clear first because it can be it's not a big deal. You can if you understand this you can do yourself only. You don't need a tool. So you see this is again
Hmm.
taken from the Gonzalez book. How easily it can be done, or I guess in ADS inside it is done by the same thing, same way. So let's see, this is a 50 ohm load you have to match. And input side, you have some input Y in, Y, Z in. Let's say this is our input side. And we have to match here. So how do we do? So one way, there are multiple ways, by the way. There are infinite ways.
Hmm.
So one easy way is that we first go, let me get the pointer again. Yeah. So from this point, we have to come to here, at the center. There only we will get match.
Hmm. Yes.
So we have to see add this stub as well as that stub. Okay, we have to design what is this length. That is what we are trying to find out. We have
Yeah.
a see 100 stub here, 50 ohm, and we have a series stub of 50 ohm. We are trying to calculate L1 and L2. Okay, now
Hmm.
how you do? See, from Y in, if we move this direction, we come to this point. See,
Right.
this length you can calculate from Smith chart. This L2. Okay, this is the
Yeah.
L2. You come here, this is the L2 we are calculating. Now, if you go there, then you have to come back here. What is this? This is adding a inductance.
Yeah.
This path, if you come here, you add a inductance. Okay. So there, what happens? You are adding inductance means this is the 50 ohm shunted stub. This length is L1. This is the L1 length. Okay. This is
Mhm.
the L1 length here, this side.
Okay.
Okay.
Uh,
Yeah. So this is not a big deal. Just understand the theory and it can be done.
okay. Okay. Yeah. Thank you.
Okay. Now yeah, this was the last slide from there. Now I'll show that how it is done there. I think I've shown you this. Yeah, the same thing was done here. Okay. So what happens? We started with this. Okay. Then the 390 ohm until this it was there already. Everything was there. So what we have added this matching network this side and that side. What I have shown you in PPT it is the same thing only. Okay. It's almost same thing. Just some modification. So the again the important thing is previous one we calculated what is the source and load resistance where we are happy with some gain and some stability. Okay. So we decided the source and load resistance from there, and then we are trying to match this 50 ohm to this the source resistance sorry the load resistance here, and 50 ohm here to the ZS or the source impedance here. That is what we are doing. So the same thing as we showed you here, this side you have multiple options to do. Now your task is to find out what is optimum for you. Okay. Here we have chosen a high impedance line for inductance, and it needs a choke and bypass capacitors. See, these all RLC values, series RLC values, it represents a capacitor. Okay. Bypass or a blocking capacitor. Here also, both side is there. So only thing is this is a transmission line, shunted transmission line, and this is a choke. So now if you see, yeah, this is the value. So when all are done, you have to again do the calculation of at every step. You have to remember that you have to check every step the matching as well as stability and the gain. Okay, see here we checked again after do the matching is stability is still there because it is at 1, it is at no the 1.002. And reflection, as you see, S11 is quite good. S22 as at the brink, but it does not matter much because S11 is through at the port, the input will be going in. Okay, so this is where it is good, quite good. And now that this portion is done, now we'll come to the what is defined for the load. Defined for the noise factor. It is quite simple. If you have understood so far, the figure circle is not much of a different thing. You have to add another layer of circles. That's all here. Okay. Okay. Yeah. Now let me show you one more important thing. Yeah. See this one here. This amplifier here or this transistor here actually has a inbuilt non-linear model. So that's why if that is available, you can actually do a whole circuit here, current, biasing, everything in the DC analysis you can do. Okay, so there you can find out what will be the you know your best biasing condition for yourself. Those all you can do yourself if it is available. But the thing is, most of the cases you won't have it. If you have, you are lucky. I saw Skyworks transistors are quite good. They generally give the nonlinear files or even all the other files separately. So you can, if you are interested in analyzing one of this, you can actually look into Sky 65050. I think it's a low noise HEMT. You can look into that. So, as I told you, there will not be any assignment for here. But if you want to learn, yourself, I will suggest you start from something here itself. I mean, not this one, previous one. What you get from ADS database, you do it yourself, and then you move to a more practical or available like a Skywork transistor. So just to show you here, so if nonlinear model is available, you can do all this DC analysis also. What we have not been doing so far. Okay, because we have a linear model which gives us a S parameter model for a particular voltage and current. So yeah, this is a just analysis what you get from S parameter model and the nonlinear model. There won't be much difference, I suppose, but there will be some. If you want very precise calculation, there might be some difference. Okay, so coming back to our, let's say we stick to this linear model, or for a particular, VC and IC, I mean, for a particular bias condition. So now what is the additional thing for noise figure or low noise amplifier calculation is that we do the same steps, but now we add the noise also, noise calculation also. So how do we do that? So the more fundamental difference here is this. Here, as you see, there is only S parameter data, no noise figure. But if it is LNA design, you have to find a transistor where with this one you also get a file where you get a frequency versus noise figure data also given. That should be given here. So I saw some of the transistors are given have that. They will be giving you, or even in the data sheet, you will find a similar table where frequency versus noise figure data will be given. So when you when it is added here, let's say this transistor has added, you can also look into this NE68139. You do the same S parameter calculation. Only thing is now you have to enable the noise figure calculation here inside this calculate noise. Sorry. So when that is enabled, now you will get the noise also inside. Now see what is there. Sorry. So coming back to this, yeah. So now, as you see, so now we have even more circles. Okay. The interesting thing is in the Smith chart, previously we are having only gain circles. This calculation, these tables, right? Now what we are adding on top of this is the noise figure circles. That is what here. See, in the same way, you have to add a noise circle. Here you don't get frightened by seeing lot of stuffs. You don't need all of these actually. You just have to put one gain circle or maybe two gain circle and two noise figure circle. So the same way you can put the noise figure circle also here. You see this one here and this one here. It represents 1.5 dB noise figure and 2 dB noise figure. And these are the gain circle, MSG minus 2, MSG minus 1, similarly, okay. And we have also the stability, source stability circle here. This side is the source stability, okay, this one. So now that means we are operating at this zone, okay. So now thing is, you have to choose some intersection point between the gain and the noise figure circles where you want to operate at. Previously, we are choosing only the gain circle and stability circle thing. Okay. Now here you have to take care of all three: stability, noise figure, as well as gain. You have to choose a point. Let's say this point we choose. Okay. Where we have our desired optimum noise figure, optimum gain, as well as it is stable. So when you choose that point, then rest of the things are again same. You choose let's say this is the point you choose here. Okay. This point. So now from this point, you can again determine what should be the gamma S and gamma L, source and load reflection coefficient, and accordingly source and load impedances. When that is done, then again you design the matching network. Those steps are all same. Only thing is here extra stuff is you have to now plot the noise figure circle and see where you get your the overlapped or the optimum point where you get all three: gain, noise figure, as well as stability, source and load stability both. When you get that, then you can go back to your again matching network design. That is all. Otherwise all the rest of the stuffs are same. Is that now understood?
Sir,
Yes.
suppose if the stability circle is outside, then
Hmm?
gain circle is inside and noise figure circle is inside.
Okay.
Can we take like that, or else we have to
Huh,
include
yeah,
both the
see,
three?
as I told you, if stability circle is outside, that is the best case, right? If stability circle is more inside, that is the worst case, or that is the bad case. So optimally, that's why you see here, if you see stability circle is inside little bit. Okay. So this overlap zone is actually it is unstable. Beyond this, it is stable. Inside this portion is stable. So now the thing is, that's why we are adding a center resistor
No,
so
actually,
that
it
this
should
will
be
be this. That's why it should be at the boundary. Yeah.
no, no. Like now, the source stability circle is the red trace, right?
Uh, this one.
Red arc.
This one.
Uh, So
Yes.
our stability zone will be normally like unconditionally stable zone is greater than that part.
So see, the don't go into greater than or less than. The
Mm.
easier way to understand, as I showed you, inside the stability circle is unstable. Outside
Mm.
it is stable. Okay. Now you
Yeah,
can
yeah.
understand from here. Okay. Hmm.
Yeah, now actually, if we see those circles, what I think
Hmm.
what his doubt was like if it is inside the circle now, that is unstable. Okay, inside the
Unstable.
circle means inside that stability circle,
Smith
you mean
chart. Inside, no. If
inside the
the
Smith chart.
exactly. Yes. Yes.
Yeah. So now, if we consider like a particular gain and we choose a gain from this gain circles available,
Mm-hmm.
like
Mm-hmm.
maybe our circle minus 1 or 2, and if we
Mm-hmm.
try to also achieve a particular noise figure of 1.5 or 2 dB, so in
Mm-hmm.
that case we will be missing out the stability. That's what I think he also asked. I also feeling that like now
No.
for getting stability maybe then we have to add some resistance as you said,
Uh,
in
uh.
shunt or something, right? And
No, no,
so that
see,
that point will be
no, no,
shifting.
one point. See, at this point, what are you missing? See, beyond this is the stability circle, okay? So beyond this, inside the Smith chart, we are stable, okay? We are conditionally stable. So now if we choose any point here, let's say this is the point we choose here, okay? Or even this gamma optimum point, this point if we choose, here we are safe, right? We get some gain, some noise figure, as well as stable.
Okay.
Is that clear?
Means like conditionally
Oh,
stable.
Condition is stable, yes, yes.
Yeah, that's what by adding some kind of resistance or something,
Ah,
we'll make it stable.
stable,
Conditionally
stable.
stable means.
Ah, yes,
Okay.
yes, right.
Yeah, it's clear. Thank you.
Okay. So yeah, so far this is the thing. Okay. This is, I will say it is little bit complicated. You have to give it much, more time to understand, go through the theory first. But it's always these resources will be there. I will upload to the resources and all. You can look into this again and you can follow these references and all. It's very good. And the Puzar book is always good. And always I will I also ask you that first go through these steps, what is in their ADS itself, start from there, follow this the same, understand yourself, and then go to your whatever you want to design. Okay. So this has been so far, this is actually the end of my class, or as even for this completion of this course also. So yeah, thank you all for attending. I will ask even some feedback for you now. If you have some time, please give me some feedback. Or even I guess I never had an introduction from you guys. So can you one by one tell me where you are working and what you are up to now, and how the course was important, and or how I can do better or I could do better. Just if you can tell me 1 2 words because we are going to end it today. So yeah, maybe I
sir,
will. Yeah, yeah. Prem. Yeah.
do you are you planning to conduct the class again?
Again, in the sense, just let me.
This course again?
No,